The next two lessons are going to cover significant figures. The first lesson, this one, we'll discuss what a significant figure is, and then in the second lesson, we'll talk about the arithmetic with significant figures and rounding your answers so that they have the proper number of significant figures. At this point, you should have already completed the activity in class on measurement. And so I hope you realize that significant figures are nothing more than measured values. When we take a measurement in lab, all we are doing is assigning numbers into certain place values that you learned in first, second, third grade. Now the rules you see below are ways for you to look at a measurement or a number that you're not sure is a measurement or not, and just read a number and tell how many significant figures there are. In other words, what kind of measurement was it? So I've made 5 columns here, one for each of the rules. I'm going to read through the rules and then give you some examples of what they're talking about. You should make a copy of these rules, and we'll use those as we go into the next lesson on arithmetic. But rule number 1 says non-zero digits and zeros between non-zero digits are always significant. So what we mean by non-zero digits are like the number 1, the number 11, the number 252. In each of those numbers, each digit is significant. If there's a number there, that indicates a measurement has taken place. And then the second part of that is zeros between two digits. For example, if we have 205, we always know that non-zero numbers are significant. They are measurements. And if you think about it, if a zero is in between two measured values, how can it not be measured? So zeros in between two numbers are always significant. So here, there are 3 sig figs. In the number 1001, how many sig figs do you see? Yeah, there are 4. 1, 2, and if those are measurements, then these 2 also have to be measurements. And then the decimal doesn't really affect that. If we have 10.605 and we want to find the number of sig figs, well, of course 1, 6, and 5 are non-zero, they're significant. So then this 0 here is between two measurements, therefore it is significant. And then same thing with this 0 here, even though it is between a 1 and a 6 and there's a decimal, we don't care. So in this number there are 5 significant figures. The next rule is also fairly easy. Leading zeros are not significant. So what we mean there is, like for the number 2, there's 1 sig fig. There is an infinite number of zeros to the left of the number 2. And these zeros all represent place values that are unmeasured, unfilled. They are insignificant. They are placeholders. And with any number, with the number 50, again, there are an infinite number of zeros out to the left. And here's where it gets tricky. With decimal numbers, I'll just say 0.54, there is a 0 that we typically write just to the left of the decimal. This 0 is also insignificant. It is not measured. Most people think that just because there's a decimal here, that any 0 that pops up is significant. That's not true. I always tell students, don't start counting until you see the first number. So if we have 0, 0, 0, 3.25, as I read it from left to right, nope, nope, nope. Oh, there's a number. There's my first sig fig. So then those numbers will be counting also. So remember, there's an infinite number of zeros to the left of any number, including decimal numbers. And as this last example shows, the 5 is the first number. None of those 3 zeros count, because they are called leading zeros. The third rule is one that can lead to confusion because the decimal point really breaks Rule 3 into a kind of a part A and a part B. Let's talk about the first part of it, zeros to the right of all non-zero digits. Well, we're talking about like the number 500. In the number 500, there is one sig fig, and these 2 zeros are each insignificant. In the number 20, we see the same thing, insignificant. And it's kind of hard to explain, but you have to change the way you think about the measuring device here. In this case, you'll be measuring something, and the measuring device is constructed so that it doesn't make a reading, or it doesn't have the ability to read anything lower than the first place value that you see. So what does a decimal do? If I take a decimal and put it behind the number 20, well, that changes the game entirely. Now I am indicating, I'm very clearly communicating here, this decimal tells you that the 0 that followed the 2 was measured. It is significant. So the decimal can imply significance in certain situations. Here's another example. If we have 20.0, again, the decimal is going to imply significance. So this 0 is significant, and so will this one be. All end zeros are going to be significant. All end zeros are significant when there's a decimal. And we could play this game for a long time. How many do you see there? Yep, the answer is 1, just the 5. Let's put a decimal. How many do you see now? Yep, there's 3. Now the 2 zeros count. Let's put a 0 on the end. How many now? Yep, there's 4, because now the end zero after the decimal indicates. Alright, sorry about that, I was attacked by a fly. So this last 0 indicates a measurement, so now there's 4. And then if we put another one on here, holy smokes, now there's 2 zeros after the decimal. Do they all count? Absolutely. So now there are 5 significant figures. If I put another one on, how many do you see? That's right, now there are 6 significant figures. The decimal shows you that significance is implied. The final 0 after a decimal is always significant, and then you just refer back to rule number 1. Any zeros between 2 sig figs are going to be significant. So one last practice here. Let's do 201.010. How many sig figs do you see in that number? If you think there are 6, you are correct. The final 0 is a significant 0. And then really I'm going to stop at number 4, I think. I've had some time to think about it. For values written in scientific notation, we talked about that a bit already. Scientific notation has one purpose really in science, and that purpose is for large measurements or measurements where the measured values are in very large place values. Scientific notation separates numbers into placeholders and sig figs. So the standard form for scientific notation is sig figs times 10 to a power, and those are your placeholder values. So when I write a number in scientific notation, 5 times 10 to the 4th, any number that you see over here had better be significant. In that case, there's just 1, so 1 sig fig. If I do 4.0 times 10 to the 4th, this time there are 1 and 2 sig figs. Zeros at the end of decimal numbers are significant. It needs to be. If it's there, it better be important. In math, you might have learned that that you always put number, decimal number. Like if you go back to problem number 1, some of you would think automatically that you would need to write 5.0 to be in scientific notation. Well, that's not true. Number 1, this first example I did is perfectly acceptable if 5 is your only measured value. If you want to put 5.0, then the 0 better be a measured significant value. The same thing applies for negative exponents. If we have 2.50 times 10 to the minus 3, again, we don't really care. The 10 to the minus 3 implies that we have some leading zeros in front of the 2 going this way. And so the only sig figs in this measurement are the 3 shown on the left, 2.50. Okay, again, print these rules out. We're going to use these rules to practice here as I change slides. Okay, here's some practice. If you haven't yet, hit pause, print this sheet out, and answer every question. Then I'll go through it one by one and talk about the correct answers and why. All right, let's have some fun with this. How many sig figs do the following numbers have? Well, in number 1, there are 4. All numbers count. In number 2, if you look carefully, there are just the 2. These 2 here. These zeros are what we called leading zeros. They don't count. Don't start counting until you get to the first number. In number 3, I count 8 and the 9. And this 0 here, there's no decimal, so there are only 2 zeros at the end are not important unless there's a decimal. In number 4, the 9, the 1, and then rule number 1 says that the 0 between those count, so there are 4 sig figs. The 0 at the end does not count, just as it didn't in number 3. In number 5, I hope you put that there are 5 sig figs. The decimal there changes things. Zeros at the end of decimal numbers count. In number 6, there are 8. The decimal makes this 0 count. In number 7, a lot of people will probably miss this. There are 3 sig figs. Of course, the 1 and 2, and then the decimal makes the 0 at the end count, but these are all leading zeros. They do not count. Number 8, we have a number in scientific notation. So any number to the left of the multiplication sign should be significant. They're both numbers in this case, so there's only 2. We don't care about the placeholders. Same thing in number 9. We don't care. There are still 2 sig figs. In number 10, we have an attempt at scientific notation. It's in a little different form. It's perfectly fine. All 4 of these are significant. And our rules back that up. This 0 is important at the end of a decimal number. Important, and then a 0 sandwiched is important. In number 11, there are only 2. The 3 and the 0 at the end. All these things here are leading zeros. In number 12, we start with a 1 and end with a 1, so they count, and everything in between those count, but the end 0 does not, so there are 6. Careful with number 13. If you miss it, there's a decimal at the end here, so all those numbers will count, so there's 3. In number 14, there is no decimal, so it's just the 1 that counts. Only 1 sig fig. Just a few more now. If you missed a bunch, why don't you go ahead and hit pause and redo the last 6 to see if you fixed some of the mistakes you've made. All right, let's finish off these last few. In number 15, there are 6 because the 0 at the end counts. In number 16, there's only 1. Just the 1 counts, leading zeros. In number 17, we also have leading zeros. There are 3. The end 0 counts after the decimal. In number 18, there are 3. This is the 0 at the end without a decimal. In number 19, there are 4. And finally, number 20, There are two. All right, I hope you understand this. If you don't, come see me, and let's sit down and do some additional practice together.